Hello and welcome back to Calculus 3, section 12.5, chain rules. So, pretty much every problem could have a different formula if we use different number of variables. So we're going to go back to Calculus 1, review the basic idea, and then upgrade to what we need in Calculus 3. So going back to Calc 1, with K's obviously, right? We are going to deal with the function composition. So we have f of g of x. And an example of that could be, let's say, sine of x cubed. So we can see that the outer function, the main function, is sine. And g of x, which is plugged inside, is x cubed. So this is your calculus, this is a pre-calculus skill to decompose composite function. And then Calculus 1 proposes the formula, let's have that, let's say blue, where to take the derivative of function composition, you take the derivative of f. So, hold on. To take the derivative of function composition, you take the function of f with g plugged in and you multiply it by the derivative of g, right? So that was the formula. Maybe I can use, let me use the the Leibniz notation here. So here, d dx. There we go. Now, what does that mean for our example? Where if we are trying to take the derivative, again, this is still Calculus 1, the derivative of sine x cubed, we are going to take the derivative of the outer function, so the derivative of sine is cosine, with g still plugged in, and then in a chain, we multiply with the derivative of the g, which is the inner function, and then you can simplify this as 3x squared cosine x cubed, and that would be the end of it. Now, if you had the nested functions, the chain rule will just add another derivative and another derivative and another derivative. So I want to also show that case. So let's say that you have d dx of sine squared x cubed, right? So now in this case, we have three functions that are nesting. So the overall function, what's the main f of x, the most outer function? What would that be, looking at this example? X squared, very good. It's x squared. Because this square over here crowns over the entire problem, right? You can rewrite this as sine x cubed, everything squared. So you see that, you know, replacing this with x becomes x squared is the main function. And then we dig deeper, right, the layer in, that would be sine x, and then another layer in would give us x cubed. So now you can test this going back, plug this one for x, plug the entire thing for x, and you would see that it works, right? So that was the idea of this. So now we can do this by saying that the derivative of x squared is 2 times what we had over here to the first power. I don't have to write it. Then the derivative of the inside, so times cosine of x cubed, and then finally the derivative of x cubed is 3x squared. Students sometimes also ask me, well, how do I know when to stop, right? Because clearly if you go over here, you can still write 6x and then write 6 and then get 0 and kill everything, right? If you overdo it. So how do we know when to stop? Well, it's here, right? You have three functions, 1, 2, 3, and then you have 1, 2, 3. I mean, that's that. So that's when you stop, when the number of functions match the number of the inner derivatives. Because as I said, can you take the derivative of this? Yeah, you can. You're not supposed to, because you are actually supposed to take the derivative of x, and that derivative is actually 1. So, yeah. Anyway, that's that. Let's switch to Calc 3. So now, why is it plural? Why do we have many chain rules rather than just one like in Calculus 1? Well, we have it because the number of variables in Calc 1 is limited to one variable. So you can only have nesting within one variable. But in Calculus 3, you are dealing with a multivariable function that can branch into as many variables as your application needs. For instance, the BMI formula, right? The body mass index. What are the variables? Height. That varies within the people. Obviously, weight varies between the people, right? And then age is also in the formula. So when you're looking at the body, I can pull it up and see. If you look at that formula, it's a multivariable calculus formula. Sure, it, calculates the simple concept, but, right, if you want to find the total derivative in respect to time, because your age changes in respect to time, that is time, the weight and height, everything changes in time, right? It makes sense to find the change of BMI in time, where every other variable depended on that time to begin with. So now we have to understand that in Calc 1 we just had y equals f of x, and then you had y equal f of g of x, and y equal f of g of age of x, and you can nest as many of them, but see that x is the only variable. So you can have only one chain rule, one long string. I don't care if you have to do 20 chains, but it's the one chain rule formula. But look at this now. Remember that your z is equal to f of xy, right? So you have this. And sure, you can take partial derivatives. But now you want to do some nesting. And what I'm going to do is I'm going to make these x and y functions of, let's say, common variable t, time. So x and y, which are location in space, x and y, which are location in space, are going to depend on, right, on the time passed, right? Because at 1 p.m. I wasn't in this chair at 1 p.m. And now it's, what, 6:21? I am in this chair, right? So with progression of time, the location, which is the xy location where I am, changed. So it's easy to imagine that, I would hope. So now what I'm going to have is I'm going to have that x is some function of t, and y is some function of t. Well, great. I can draw a tree diagram that branches my z into two variables x and y, which together make z using a rule, whatever we assign the rule to be. And then this x and y's depend only on t. So as you are looking at this tree diagram, you can see that t gives rise to x, gives rise to z, and also t gives rise to y, gives rise to z. Now both x and y together make z. And this is the part where Calculus 3 is. This is the part where Calculus 1 is, right? So there are two layers to this. Okay, so let me write the formula. What happened? What happened? Oh, na zdravlje. So let me find the derivative of z in respect to t. As I'm looking at this, right, clearly I have to get all the way here to have dz dt. But then also if I go the other way, I will have dz dt at the end. Okay, that's fine. But see, the trick is that I have to go through x and I have to go through y. Now, when you run into the split, that's Calc 3 and that's Calc 3 derivative. So, partial z, partial x. Because there is a split. Times dx dt. that is Calc1 derivative. It's a straight through. There is no split. X depends only on t. Plus the other branch that also contributes to this derivative, because the z will change in x, and it also changes in y. So we are going to add the more of the change that happens. Again, it is a partial z, partial y, because it's a fork, it's forking, it's branching, whatever you want to say, right? And then you have dy dt straight through. Y only depends on t. And this would be the formula for chain rule when you have two variables, x and y, right, independent variables x and y, that actually depend on parameter t. It's a function of position, right? All right, so this is cool, right? Now, in which ways this gives rise to plural chain rules? Well, what I'm going to do, I'm either going to increase the number of variables in terms of x, y, z, w, blah, 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 or I'm going to increase the number of parameters on which x and y and z depend, or both. And you can quickly see that we can make technically whatever, and every time when you mess with the number of either of the variables, there will be a completely new formula that you have to develop yourself. There is no chain rule formula in Calculus 3 like there is a chain rule formula in Calc 1 that you memorize and go solve all the problems. Here, you have to draw the tree from what you see, and then you develop the formula from the tree, and then you solve the problem. So welcome to Calc 3. Here's another example of creating the formula using the tree. I'm going to keep number of variables x and y at 2, but I'm going to increase the amount of parameters that they depend on. So I'll make dependence on t and s. So now, if I want to draw the tree, the main variable z, right, our final goal, right, to find, let's say, the height, is going to depend clearly on x and y. But now, if you look at the function on the side, you see that both x and the y depend on t and s. Ooh. Everything branches over here, right? Now, what would be dz dt in this case? Well, first of all, you see that t's are these final destinations. S's are also final destinations, but no one asked for dds. So we are just considering branches of the tree which end in t variable. So you have to start from z and propagate through tree, in this case, until you reach t's only. All right, that's cool. So let's do it. There is a branching at z, so partial derivative kicks in, right? We have partial z, partial x. And now we need to jump to t, and there is branching again. So partial x, partial t. Plus, there is one more branch that gets me through t, different path. Partial z, partial y, partial t. And that's the end of the formula. I have reached the destination, which is t, through the tree, right? Following the paths. Now, observe the chain rule, right? If you are to cancel the x's, you get dz dt, cancel dy is dz dt. Cancel the x's, dz dt, cancel dy's dz dt. If you are any good with dimensional analysis in physics, you will spot that immediately over here. Let's just quickly look at the formula in physics where y equals to negative 1/2 gt squared plus v0t plus y0. If you are trying to remember the formula, you can't, you're missing one little piece, dimensional analysis helps you figure out what the piece is. Because this thing is given in meters or feet, let's use feet if you like it better, and this thing is equal also feet. Well, the formula better be feet is equal to feet plus feet plus feet. You can't go seconds plus kilograms plus, that makes no sense. You can't go to the store, take 3 bananas and add 2 minutes to it. That makes no sense, right? It's absurd. I mean, half of the classroom is smiling now because it's so absurd to say it, right? 3 bananas plus 2 minutes. What do you get? It has to be 3 bananas plus another 1 banana or whatever, and you have, because you're adding mass, right? So you have to add all of the same units at the same time. So now, okay, gravity is going to be feet per second squared, and time is in seconds squared. Second squares dies, and you just have feet there. Plus velocity, feet per second, times the time, second, kill that, there's feet. So feet plus feet plus feet equals feet. That's called dimensional analysis. You can use it in general chemistry and just do this with those courses because they're literally nothing if you know this. They give you units in a word problem. And all the formulas are triplets. Entire chemistry 1 and 2 is sitting 15 minutes to figure out reactions. It's 1 chapter out of the whole thing. If you know this. That's how joke that stuff. Organic, I would never touch it. That's not for me. That's for your beautiful brains, right? Who can process that kind of information, right? I need equations and order, right? Now I'm going to use this particular thinking, right, that you might adopt from physics if you know it, to go here, and every time when I write the formula, I just need to make sure that my dz is equal to dz when that dies, dz when that dies. And in every formula you write, you must have that. Anytime when you do the cancellation, if what remains here, and I can have 15 of these, they all have to cancel. If you get dz dt somehow, and ds on this side, wrong. You have the wrong formula, and you have to go back and figure things out. Now, I also promised the plural thing. Well, I have another variable here, and that's the blue path. The blue path of going from z into s and z into s. And that path has its own dz ds. I actually used the wrong d's over here because there's branching everywhere. There we go. So dz ds. Follow the blue path. Partial z, partial x because of the branching. Partial x, partial s because of the branching. Plus because there is another branch. Partial z, partial y, partial s. Chain rules, it's the same problem, right? These formulas are different. They use different variables, right? Parameters, in this case, t and s, right? So you are going to have multiple formulas for the same problems, depending on what is needed. Yes.
Can you scroll up to the first box? So why is it dx dt over there and not partial?
Probably I missed something somewhere. Where?
The first box.
This one?
Yeah.
Oh, because, look, This is calculus 1 situation where dependency of x is only on one variable t. You use partial for branching, right? And regular d. First of all, you will never make the mistake if you use partial derivative for everything, because partial derivative is the concept that also under its umbrella is taking the strict one, which is the regular derivative d. So if you use partial everywhere in every formula, you won't make mistake, but it will be kind of, you're not used to seeing it, it will be weird for you to say, okay, you have that x is, 2t cubed, and you're supposed to find partial x, partial t, right? You are used to kind of have another variable that you ignore, right, if you have partial derivatives. So that's the reason. However, it's perfectly fine to use it because this will still be 6t squared. I mean, if you use this notation, not a big deal. OCD kicks in and then we're all, as a species, make our peace that there is a d and then partial d. Let's take a look at another example because we can. So say f of x, y, and z. So that's your w, right? So w is a function of x, y, and z. And let's say that your x is a function of t, s, and r. Just t and s is fine. T and s. Y is the function of just t. And z is function k of just s. Let's say this is what you have. Can you draw the tree for this? Well, just follow the branching, right? You start with w, and that branches into 3 variables, x, y, and z. Now, x branches into t and s, y is only t, and z is only s. So, please stare at this and make sure that you can 100% do this, right? After that, if you are able to do the branching correctly, writing formulas, you use partial derivatives for branches and regular d's, derivatives for straight through. It should be easy to write any formula. We're just learning how to write the formulas. We'll do the problems once we know how to set up the problems. All right, let's write the first formula. Let's say I want dw dt. Remember, start at w in the numerator, end with t in denominator. So there is a path 1 ending at t and the path 2 ending at t. Observe that z does not depend on t. I'm not going to waste my energy writing anything there. Great. Branching. Partial w, partial x, times branching on x, partial t. I have another branch. Great. Plus partial w branching, so partial y. And now straight through, right? dy dt. Yep, because y depends only on one variable, and that's your calc 1. Branching, calc 3, partials. No branching, calc 1, single, b. Bueno? Cool. Time for the blue path. partial W, partial S. You do it.
That's just a nomenclature, so if you're not doing anything different from dy dt, it's partial y.
Well, we're going to take these derivatives once I give the functions. This is us learning how to write the formulas.
I mean, just the nomenclature of the b and the partial. So for that dy dt, you're doing the same thing.
Yes, you just don't have other variable present that you have to worry about, right? When you have partial derivatives, that means other variables are there as well, and you have to treat them as constants. Where the regular derivative just in the presence of one variable, so the other variables are not going to be there. All right, so create the blue path for dw ds. See you next week. You too. Time for the blue path. I have, again, two paths that create will connect W with this case S variable. So there will be a path going this way, and there will be a path going this way. So dW ds is partial W, because we are going to have branching. Partial W, partial X, partial X, partial S, plus branching again, partial W, partial Z, and then regular dz ds, because it's just a straight through. Now, I'm going to give you a problem which we will have to consider. So let's say z equals ln xy minus 3x, where x is equal to 2t plus s, and y is equal to s squared. That's it. So this is what is given to you. You are supposed to find dz dt and dz ds. Now, you are looking at functions now. And if you can read the tree and make the tree looking at the raw problem, great, do it. If you need this type of a map, you will have to create that map first by looking at what's given to you. I should say that it's clear that z is the function of x and y because z depends only on variables x and y. And then also it's clear that x is a function of t and s because it depends on both of those parameters, and y is the function of s alone because it's just s squared. Are we all able to do this by looking at the formulas up there? So z has only x and y as variables within z, so function of x and y. X has both t and s as variables, so there we go, and y has only s as a variable. Once I have this thing, I can draw the tree, and then I can finally get the formulas so I can start calculating this thing. So the tree is z branches into x and the y, x branches into t and s, and y only goes to s. What happened?
Or x equals to t plus s.
Plus s, yes.
Will you get that from again?
That's given to you.
Oh, that's given.
Yeah. The whole thing over here, this is your statement of the problem. Okay? This is the problem statement, and that's all given to you. Anything under the box currently is what we are writing to solve the problem. So I have a tree, and now I can go and follow the red path from z to t, and there's only one branch, right? So there will be no plus, there will be only one term. Great. What is the dz dt? Dz dt is partial z, partial x, and then partial x, partial t. And that's it. There's nothing else for us for this particular formula, because it's only one branch which starts at z and ends in t. Are we agreeing on this? Good. So now, what is the answer to my question? Well, dz dt is equal to, and now you do partial derivatives. What is partial z, partial x? Well, you just do your regular stuff. Partial z, partial x, that has to be 1 over x, right? You have xy on the bottom, and then chain rule kicks in and puts y on top, and then minus 3. So this is your dz dx times dx dt is just 2. So this parenthesis here is partial z, partial x, and this parenthesis here is partial x, partial t. All right, so now it's time for you to go a little bit cross-eyed on this, collect where the stuff is. The formula commands to get dz dx. Great. Dz dx. So partial over here. ln is 1 over x. So derivative of ln xy is 1 over xy, and then times the chain rule, Calc 1 chain rule kicks in, so y goes on top, and then they cancel eventually. And then the derivative of 3x in respect to x is just negative 3. So this is the partial dz dx. And now you need the partial dx dt. Well, where is the formula that connects x and the t? It's this one. So what's the partial dx dt? S is a constant, derivative of s is 0, so that dies. And you have dx dt, so it's just 2. Now observe that your answer is, well, and then I didn't cancel these y's, now y's are down. And the answer is to be in respect to variables s and t, right? You can't have this. So what you do is you plug in what x is. So what is this dt? The zdt is going to be 1 over 2s plus t. No, 2t plus s, right? 2t plus s. Oh, times 2 and minus 6. That's that. And here's your answer in terms of t. This is what you box as the end of your problem. Yes.
So even though it's with respect to t, you can still have like other variables in the.
Yeah, it's governed by the problem.
Okay.
Nothing you can do about it. We are going to do the s now. So we'll see. So what is the dz? ds. Those are my blue branches over here. Partial z, partial x, partial x, partial s. Because there's branching everywhere going on a first branch. Plus, because there is a second branch, and that's going to be partial z, partial y, and then regular dy ds. It's a straight through shot. So we use the tree to create the formula for our partial derivative, and then we just go and solve each of the pieces looking at our formulas. So the first order of business over here is to find the partial derivative of z in respect to x. I already have that. That's my 1 over x minus 3. And now I need partial x, partial s. Partial x, partial s. Partial x, partial s comes from the formula that connects x and s. And that's just going to be 1 in this case. So, times 1. Plus partial z, partial y. Alright, partial z, partial y. This is the formula that connects z and y. And when you do partial in respect to y, you will get x over xy. So it's just 1 over y. The minus 3 dies because there's no y there. So this becomes 1 over y only. And then times the derivative of formula that connects y and s, which is this one, and straightforward calculus 1 derivative of that is just 2s. Simplify. Partial z, partial s is equal to 1 over x minus 3 plus 2s over y. Plug in x and y. So partial z, partial s is equal to 1 over 2t plus s minus 3 plus 2s over, and y was s squared. Now those cancel, s and a square. And the final answer over here is 1 over 2t plus s minus 3 plus 2 over s. Yay, huh? So much fun. You have to figure out the formula first and then do the problem. Well, let's take a look at examples that the book is providing. This is problem number 10. They are looking for dz dt, where z is given as x squared y minus xy cubed, x is given as t squared, and y is given as t to the negative 2. Have fun.
This video when I get home. Right? Awesome. See you on Monday. Yeah, and then I gotta quiz someone more tonight. You know.
Marissa. She's stressed. She hasn't taken math in a while, so she's like, she's at tutoring center now, but
Depending on you.
she's not getting.
We're all gonna blame you
Why?
if it doesn't work well.
It's on her. But,
Yeah, it's kind of cool. You know, I think about it, I have a couple of languages a year, and I just really look at it, but it's going to bump around.
quick question. When you have x squared over x squared, or for horizontal asymptote, isn't that one of those things where it just equals 1? Because it was on the quiz or the homework. Because x squared over x squared.
Yeah.
That would be 1, right? And if it has coefficients in front of it, you just take them. Right. But she said her lab person, one of her lab people said it was 0. Yeah, it was 0. That's what they're going to put on the lab. So I gotta go tell them it's 1. So, alright, let's see.
Okay, I'm going to draw the tree from what's presented here. Z depends only on x and a y, so there is branching there. And then x depends only on t, and y depends only on t. So this is a very first example we did in class, and the tree and the formula from that chain rule is the one that we have to use. I am going to have only the red path in this case because it ends in t, and again it ends in t. So the only one formula. So the derivative in respect to t is partial z partial x because of the branching, it's partial, and then dx dt straight through. Again, as we want to check this, if you cancel dx's, you get your dz dt. So we're good there. There is another branch, so plus, and we have dz dy, that's partials because of the branching, and then dy dt. Again, if I am to cancel these, you get that the dz dt is dz dt plus dz dt, so we're good on formula at least. Now I'm going to use the formula. dz dt is going to be partial in respect to x, so that's 2xy minus y cubed times dx dt, which is just 2t. Plus, now I have dz dy, which is x squared minus 3xy squared, and then dt, right, is going to be negative 2 t to the negative 3. Now we need to simplify all of this, and that algebra obviously is a bit annoying, but that's okay. We have 2. Instead of x, I'm writing t squared. Instead of y, I'm writing t to the negative 2 minus t to the negative 2, everything cubed. Everything times 2t plus t squared squared minus 3t squared, and then t negative 2 squared times negative 2 t minus 3. So now these guys cancel to 1. So all I have is 2 minus t to the negative 6. And then everything this times 2t, that's next step, plus open parenthesis t to the fourth minus this is 3t squared divided by t to the fourth, because you have, this is not supposed to say y, it's supposed to say t. Y is t negative 2. And then all of these times negative 2t negative 3. Multiply over here, we get 4t minus 2t over t to the 6, since we'll do cancellations later. Over here I have t to the fourth minus 3 over t squared times negative 2 over t cubed. I still have work to do. So this is 4t minus 2 over t to the 5 plus, no, minus, we are distributing, 2t to the 4 over t cubed plus 6 over t to the 5. There we go. T to the 5, because 2 plus 3 is 5. And finally I have 4t minus 2t to the 5. Oh, that actually adds to the last one, so it's plus 4 over t to the 5 and minus 2t. Oh, now these combine, and the answer is 6t plus 4 over t to the 5. All right, so next time an algebra student tells you that their problem is way too long, you just flip. That's what I said, 2t. Pay attention. It's clearly 2t. Look. 2t. No, it's 2t. I mean, it's clearly 2t. That's okay. I mean, I understand you're tired. It's late. It's okay. I know. Oh, you want the next problem. That's why everyone's looking at me. What are you going to do with the superstar, you know? No matter where I stand, everyone's looking. Problems 27 through 30, making trees. We did pretty much the whole class on making trees. So please practice those in case you need more. Now let's see. Where are the... Oh, hello. All right. Go away. Question 22. They want you to find ZS and ZT. Partial derivative with respect to S and partial derivative with respect to T. Z is given as sine x times cosine of 2y. X is given as S plus T, and y is given as S minus T.
But it would be multiplied in front of it, right? It wouldn't hit. It wouldn't get canceled out, right? If it was like 5 sin x, it would still be 5 and still be like that helps. No, it's not. They don't both have x in them. So this would just be like, you just take this and just stick it over here. Just think of it like 5 or something. And then it would just be like this. That's what I think. All over the street. Like if there's a plus sign in it, because like 2 out of definitely go away. But when they're multiplied, I think they just carry it. So this way? What is multiplied? So like what I'm saying is like if you have like this would be a constant. So like, say it's just like z sine x, and instead of cosine 2r, 5, right? So the derivative of that is 5 x, right? Because the constant is still multiplied by yeah. You see what I'm saying?
A lot of them show up. Because she has the honor section, so all of them come to it.
Oh, this is the number of them. This is 4. Yeah. You know, it's a quality math course, right?
All right, so z branches off into x and a y, and each one of these branches into s and a t. So this is partial derivatives throughout. Again, use red pen, everyone, let's go, to get to s, and the red pen to get to s. Use a blue pen, which you all have obviously, to get to t, and another blue, right, over here to get to t. Follow the red branch for the red formula and the blue branch for the blue formula. So what is the zs? Zs are the red ones, which start at z and end in s. So partial z because of the branching, partial z, partial x, partial x, partial s. Branching followed by branching, all partial derivatives. There is one more branch that is red, so plus partial z, partial y, partial s. Blue form, let's solve this one first, and then we'll do the blue. So zs, which is the partial derivative of z in respect to variable s, is going to be partial z, partial x. That's just going to be cosine x times partial x, partial s, which is 1. Plus partial z, partial y is going to be negative 2 sine 2y times the partial derivative of y in respect to s, and that's also 1. So what's zs? It is cosine. Now instead of x I have to write s plus t. And then I have minus 2 sine, and I have 2 times y, so 2s minus 2t. And this would be the answer for ZS because there's nothing else we can simplify here. Following the blue path, ZT is again branching on X and branching on each one of these S and T's, so we have all partial derivatives. So partial Z, partial Y, sorry, partial Z, partial X, partial X, partial T, one more branch, so plus, partial Z, partial Y, partial S. No, partial T. There we go. To check, you cancel the dx, dx, dy, dy, and you have dz, dt, dz, dt. So that's good. All right, switching back to do the problem. Zt is, guys, partial x you already have. It's just cosine x. And that has to be followed by partial x, partial t. Partial x, partial t is also 1. Plus, we have partial z, partial y. That's this negative 2 sine 2y. And now it's times negative 1, because partial y, partial t is this formula here. The derivative of negative t is negative 1. So now zt is equal to, again, cosine x is t, s plus t, so cosine of s plus t. Minus and minus gives you a plus, so it's plus 2 times sine of 2s minus 2t. And that's the end of it. Yeah.
I was confused. When you're taking the partial derivative of z with respect to x, why does the cosine 2y disappear?
Ooh, that's times. It's not supposed to disappear. I'm going to introduce you to the feature that you don't have in your notebooks. See this feature? Yeah. The cosine 2y should go through, and then the other one has sine x. So what I'm going to do, I understand that the class ended a minute ago, so I'm going to erase everything and start from scratch, and you can go. You'll be posted in notes. So I'm erasing all of this to include the parts that I missed, but I have to write it lower so it can fit. I will see you all in on Monday. I have to change, yes, I have to change everything. I'm going to move this, because the formulas are correct, obviously. I'm going to move that down and deal with that later. I'm going to fix everything now and upload the notes. See you all on Monday. Very good. I was testing everyone.
Have a good night.
Yep. All right. Night.
See you.
See ya. And bye to the...